you have heard a little bit about what neural data could look like. I'm just going to briefly mention one particular problem that often arises in neural data analysis, which is we typically don't deal with noise very well. And if this code is really good that I like, that if you think your data is clean, you haven't looked at it hard enough. So, and that's our lab doing some archery stuff behind which we like. Neural data analysis, the big word is data, and nowadays we're collecting huge amounts of data, so it's important to know how to deal with data and how to make the right kind of inferences. And we know that data comes packed with noise, so data can be decomposed into signal and noise. We typically want to make inferences on the signal, and we want to avoid noise. Right, so the main purpose of this short tutorial is to make you start thinking about like how to account for noise in your measurements while making inferences from your data. Okay, and I want to start with some examples. These are published studies, and I'm not going to name the authors or the journal or try to give as little hint as possible. But this is a published paper, and the data is being shown here, left hemisphere, right hemisphere. There are two, of course, two axes, and I think this is MEG, evoked MEG, and then fMRI. So there's some correlation being computed here between MEG and fMRI data, and MEG and fMRI data in the right hemisphere. So they're comparing something in the left and the right, and the left p-value of the correlation, or in this case R square, is 0.2. The one on the right side is 0.005. So they make a claim in the paper, say that correlations were significant in the right but not in the left hemisphere. So nothing in this slide is actually wrong. This is a right this is a right depiction of the data. This figure is not fraud. This sentence is absolutely scientifically correct. The correlation were significant in the right but not in the left hemisphere. But the problem is that will you then say that something is present in the right hemisphere that's not in the left hemisphere? Is that inference correct? And to make that inference, you need to understand what was the noise level in the right hemisphere measurements versus what was the noise levels in the left hemisphere measurements. And oftentimes you will see, even if you read this paper accidentally, you will know that these were not done correctly. You don't make, the inferences were sort of made, they were far-fetched. They were not supported exactly by the kind of analysis that were done. Another example is here. Again, delay period, reach, reaction time, delay period activity, saccade reaction time. There is no correlation on the right side. However, if I told you that the saccade reaction time measurements were done on a faulty eye tracker or something, then you would actually not believe that data. You would say that data doesn't mean anything because the data was so noisy that I couldn't even estimate saccade reaction time. So things that we correlate to each other typically in neural data analysis are brain data, like bold responses, neural activity, neural decodes. All of them are noisy because it depends on measurement noise and noise that is inherent in the brain. Behavioral data, like task accuracy, subjective ratings, reaction times, these are also noisy. There is model predictions of the above, so you can use models like people have discussed in this course, deep neural network models, to predict some of these measurements. And those you can have noiseless situations because if the model is fixed, it is always going to give out the same sort of answers to the same question. So you can think of this as something that could potentially be noiseless. So for the rest of the tutorial, I'm going to simulate a situation to demonstrate the problem, and then I'm going to provide you a solution of how to deal with this kind of problem in data analysis. Okay? This is just a simple few lines of code. So I'm going to produce two correlated variables, A and B, and let's assume that A is noiseless. Let's assume that A is like some model prediction or something. And B is something that we are trying to estimate by repeatedly measuring across trials. So B could be like neural firing rate or like bold activity across voxels or something like that. And we will assume some ground truth here. And the ground truth is that A and B are perfectly correlated if B could be measured to our best extent, right? So this is what I'm going to do is I'm going to create an A that's a random, a normally distributed random variable, has 100 elements. You can think of this as like predictions for 100 images. And B is correlated perfectly with A. So B is like 0.3 times A. So if you plot A versus B, there will be a perfect Pearson correlation of 1. Is just the slope is 0.3. Now, let's add some noise to the estimate of B, because when we estimate B, it's not a noise-free estimate. We'll have some estimates that will be noisy. So one way to do this would be that let's assume I have 50 trials. So your number of trials is 50. And this is just initiation of the variable. But I'm going to run through all these trials. And for every trial, this B noisy thing, it's some value. So it's the true value of B, plus I add some level of noise to this system. So I'm going to simulate 50 trials for estimating B. And let's run that. And then let's plot this again. So if you look at the plot now, the correlation has slightly reduced because I added a very low level of noise. So if you plot now A with B plus low level of noise, the correlation is 0.98. And I'm plotting this with the average value across all trials. So I average the noisy trial estimates of B, and then I'm plotting noisy B with A. So this is a very good situation, and I will demonstrate what happens if you add a little bit more noise. So now I'm going to go to the next bit of the code where I add a slightly higher level of noise per trial. So let's say your measurement became very noisy, and you're adding more noise. And then the correlation starts to deteriorate. Like it's not at 1 anymore. It's not at 9.9. It starts to become like 0.8 or something. Now there's another situation. Add more noise, and now the correlation becomes 0.5. So although the model from where this data is being generated, B, is perfectly correlated with A, because of the measurement noise, my Pearson correlation is 0.52. Okay? So everybody is with me until here. So now let's define another ground truth. Let's say another measurement variable, that is C. And C is also correlated with A, but the ground truth of C has some random variation. So C is not perfectly correlated with A. That's the ground truth. So my inference after I do this experiment should not be that C is more correlated with A than B, because the ground truth in the way I'm doing this is that C is less correlated with A than B. Okay? So let me plot C. So by default, C has a correlation of like 0.59 here in this case, right? It's already higher, if you see, than 0.52. So if I just ran C the way I just did, I would have, if I just looked at the correlation, I would have claimed that, oh, C looks more correlated with A, so C must be the thing that is actually driving A, or something of that sort. Now, here is another version where I actually add some noise, but lower noise to C while estimating C from different trials. So I can do that, and it's still pretty high. It's like 0.58 again, right? So if for some reason the way I'm measuring this variable C is much less noisier, then I have a higher probability of saying that C is correlated with A than B. So that's the problem. And this problem, if you read papers, you will see that the field is full of this kind of problematic inferences where the measurements are noisy and we don't estimate the noise, we don't correct for the noise of the system. So one way of dealing with this is to actually estimate the noise in your measurement, to estimate the reliability of your signal. Okay? So how do you do that? So let's look at the data again that we collected. So this is basically showing the size of the data. So A is some vector that's 100 by 1. Noisy B is like 100 times 50 trials, so 100 measurements across those 100 images, but across 50 trials. And C is that noisy measurement, again done on 100 images, but also across 50 trials. Okay? So now I will have to have some way where I do some analysis, but then the inference ends up being correct, that B is more correlated with A, but not with C is not as correlated with A. So what we typically do is we do this thing called, we estimate the Splitoff reliability of across the entire set of data, which basically involves a bunch of bootstraps. I just keep it to 100 for example purposes, but demonstration, but like you'll increase this number more. What you do is you divide the trials. Let's say you have 50 trials. Every iteration, you divide the trials into 2 splits. Like you have 50 trials. You go from like, you randomly select 50 without replacement, and then you, take the other trials. So you build 2 sets of trials, and then you build two split halves of B, split half 1 and split half 2, and build two split halves of C, that's split half 1 and split half 2. And this is basically the mean across those trials, those individual trials that are not the same, right? So now you can correlate these two, and you can find out how correlated are my signals if I split all the trials randomly into two halves. You will see this part of code, which is called Spearman-Brown correction of split half. This was developed to account for the fact that now you're making an inference, let's say, from 50 trials to 25 trials. So you are correlating two vectors that are 25 trials long, or 25 that come from 25 trials instead of 50. So this is basically adjusting for how many splits you made. So because I made 2 splits, you can make 3 or 4 splits, or however number you want. This is just a technical detail about like how do you correct for that split. So you can almost avoid this for now, but make sure that you use it when you are using this analysis. But this is basically estimating how correlated is one half of my trials with another random half of my trials. So you do this a bunch of times, you get some mean value, and let's see what happens. So I run this, it's done, and now I'm looking at the histogram of the reliability in estimates of B. So remember, B was a very noisy measurement. So the reliability, which should be at 1, because your two halves of your measurements should correlate perfectly with each other. But in this case, they are not correlated perfectly with each other. So you set your expectation of your data in some sense, because B cannot explain itself more than 0.3. So it cannot explain something else at 0.1. Or something else cannot explain it to 1.0, not 0.1, sorry. Same with C. And now you see that C, because I did not inject too much noise, is actually really reliable, right? So that also demonstrates what the problem is. Now, we will estimate a corrected version of the correlation score, which in this case, I'll just call it noise corrected correlation. So instead of, previously I was just correlating A with the average noisy B, and calling it, this was coming out to be, I think, 0.5 something, and this was higher than that, C's correlation. But now I'm going to correct it. I'm going to divide it by the square root of this mean reliability of B. So imagine if you actually had A, which is also noisy, you would just multiply this term with the mean of the reliability of A as well. So it is not necessary that both A and B are, one is noiseless and one is noisy. Both can be noisy. So you just replace, so right now, because it's not noisy, it's actually 1. So this is like this times 1, okay? Which I can actually write it down just for simplicity, because A is not noisy. But if A was noisy, I would have just done the same thing with A and put it in. So now you see that I have corrected the problem, because the corrected scores for B are 0.94, and the corrected score for C is 0.58. And if you had done this analysis, your inference would have been that B is more correlated with A than C is correlated with A. So this is one way of dealing with this kind of noise problems. And I'm pretty sure, yeah, go ahead.
Is there an intuitive interpretation of the effect size? For example, can you think of this as what the correlation would be if both variables were not noisy?
If both variables were not noisy,
yeah,
that would be equal to the original correlation, right? Because if both are 1, then you have the
I guess I'm wondering, so I understand that you can use these to make statistical inferences, but it's nice with correlation that it would be read out and square it as the effect size. So I'm wondering whether it's reasonable to interpret this intuitively.
Yeah, you could also maybe, for example, I would show that if you vary the number of trials that you're using to estimate these numbers, you will have a different effect, you have a different reliability, and then you can almost predict how many trials you need to collect to actually have a very good inference on this data set.
Okay, thanks.
Yeah, so that's actually the next part, which is, now I've shown you that B is correlated at 0.94, or corrected correlation is 0.94, C's corrected correlation is 0.58, so B is more correlated. But oftentimes when we are running experiments and maybe you're submitting a grant application, you might have collected some pilot data. it might be useful to even use this framework to tell the grant reviewers or to tell yourself or your PI or whoever you're reporting to or whoever who cares about the truth that, look, I have estimated some variable, 2 variables for a certain number of trials, and I would need X number of trials to actually get a meaningful experiment done here. Or it could also be like number of mice that you need, or number, like that N could be anything. So in this case, I'm just going to simulate it with the number of trials. So here's the code is like, I'm just going to do the same thing, but now so I ran 50 trials. I will be running now 10 trials, 20 trials per estimate. And it's the same thing. I'm just going to plot the reliability of B if you had collected only 10 trials or only 30 trials. So if you're designing an experiment, and I think I was supposed to give a brief talk on this yesterday on experimental design, but I thought this would be a good way to bring this up here, that this is something you would consider before doing the entire experiment. Like, you need to know what is the noise structure that you're going to head into, and you can decide what numbers you're going to choose. So if I run this, it's done. OK, so this is something that you find. You find that if you plot the number of trials versus your reliability, as you increase the number of trials, your reliability should increase. This is a log scale. So let's say you are around here for your pilot data, like only 50, and you think, oh, 0.4 reliability is not that good. Because the problem is that sometimes, although these numbers are going to be much different, there are error bars associated with these which might overlap. So you actually want to have clean inferences. So you want to have as high reliability in the data as possible. So a trick could be like, if you're submitting a grant and showing your pilot data, you can say that, look, I have done this experiment. This is pilot data, 40 trials, and it looks like there's a linear trend. So give me more money so that I can complete 500 trials and go to a really good data set that from where like correct inferences can be made. Okay, so that's pretty much it. That's all, and I think I encourage you to think whatever data you're collecting during this course or whatever data you're going to use in your labs or that you get from someone in this course, think about this problem. Think about how you should correct or account for noise. And because the variables can be anything, like it can be neural decodes, it can be neural firing rate or anything. So it's almost applicable for any kind of problem. Yeah.
So one thing that seems to assume is that it's really relevant for neural analysis is that the variability across trials is noise for the specific experiments. Is that always true for neural data? Is if you're analyzing the same neuron and basically across different trials presented with the same stimulus, you get variability, that's noise? Or is it the case that there is some sort of natural variability to neural response?
So it depends on how you did the experiment. So if in the experiment you try to put the monkey in a state, or the rat or whichever animal, humans, in a state where everything is supposed to be constant and you're just varying that the trial is just being repeated, then you would not assume any other thing to seek in. So in that case, I assume that the only source of noise is something inherent in the brain. So you would then assume that that's the only source of noise, the trial-to-trial variability. But let's say you're moving your eyes around or something, then that brings another noise. But there is some way, I mean, there is a clear source of that noise. So you can try and regress that out in your analysis if you knew the source. Yeah. I mean, sometimes it becomes hard to define what noise is there. Like if you're doing an fMRI experiment, is it scanner noise or is it noise from the brain? We still don't know why brain is noisy. There are some theories, but it's hard to say like that's causal of some function. But yeah, so the data is noisy. That's the thing that we know for sure, because it does not seem to be consistent across trials. Yeah.
Do you have an intuition of how that generalized to other structured noise, for example, multiplicative noise or non-Gaussian?
Yeah, I think I did not assume any particular structure of noise in this case. I was just looking at reliability between like two halves of trials.
Measure like reliability. I haven't thought this through mathematically, but if you have like multiplicative noise, then that might be a different formula of measuring.
I don't know if that's going to be a different formula, because I think this is supposed to be sort of model-free estimates.
I don't want to, like, say I have choice gain modulation in this trial. I don't want to use this to predict like a trial that has like 0.5 gain.
Sorry, you repeat the question again? You have what?
Oh, sorry. So if the noise is some maybe like neuromodulator, and say I put the response to a choice level versus a half level.
Okay.
And I just directly predict when we say half, like I predict half of my trials using half of my trials data set. When we're measuring the reliability.
But I'm still, I think we might have to talk about this offline, but I still don't think that no matter what, like you can imagine a situation where you have two variables and you have one variable you inject Poisson noise and the other variable you inject Gaussian noise or some other format of noise. If you will have the same sort of inferences being made if you just take the mean and because this is basically saying I'm repeating the experiment and I'm not getting the same result. Set my expectation. And in your case, I'm not exactly sure, but it might be that you have to sort of cluster the trials into two separate types and then do the analysis separately. Yeah, but we should talk about this. Yeah.
So I have two questions. So the first question is, when you do that, you actually it does make an assumption that is the reliability reflects the noise of the measurement itself.
Yeah.
But if you imagine the world where you have another modulation variable that actually can modulate the value, the value you care about,
yeah.
When you do that, you actually blend in this influence into this question.
So if there is another source that is affecting the variability, it's like it's either a signal that should be, there has to be some reliable factor associated with that particular source, right? So you're saying that there's some other source that's modulating my responses. Is it doing it randomly or does it have some structure to it? If there is a structure to it, you will be able to get it out of here because whatever that is, it just becomes part of B or C or whichever variable it is that I'm measuring. So you have B and you're basically saying that I don't know about this other source that is contributing to the variance of my data. It's not measurement noise. It's like some other factor.
Okay, let's talk about this offline.
Okay.
Another thing is like when you do that actually will always bias your measurement to make it higher than previous.
Yeah.
So you don't think this is.
But if it will only go up till 1 because like you always have noisier, like it's like saying that your data can always be noisy. It cannot be like more accurate than the most like.
Once after you have done that, right? After you have done that, how long is positive bias?
Yeah.
Always increase the correlation.
No. So if you only increase the bias, that's going to be a problem. But the thing is that the variance of that, where it's going to land per trial or per split, is not going to be always high. The mean, I agree, is going to be always higher. But there will be huge variances, so you won't be able to make any statistical inferences using that data. So let's say your denominator becomes like 0.1 or 0.01. Anything divided by 0.01 is very high, right? But I think what happens is that because it's around that area, sometimes it's going to be negative. So you are going to basically go around like your main number like quite a lot. So you won't be able to do a.
So you may want to affect this statistic because the variance is awesome.
Yeah. So I think it's a conservative measure, like if you are not getting correct answers, it's better to not get any answer.